good morning, my dear students. We're going to start class different concepts. One is nanomaterials and characterization techniques. Okay. So I think in that class we were just about started with the characterization technique. So before that, so we were talking about the nanomaterials, the nanotechnology, and the different methods. What we can manufacture the nanomaterials. The methods in nanomaterials can be synthesized. So I think I started with the characterization techniques in the last class, so where we discussed two different characterization techniques. One is optimization technique, traveling electron microscopy or XRD or atomic force microscopy, like that. There are so many things there, so that we will going to discuss it now. Okay. So what we call it as the transmission electron microscopy. In this, we need to discuss what is the basic principle behind this transmission electron microscopy. Okay, and then we need to discuss what are the imaging modes, and also we need to discuss how we can use this transmission microscopy in different applications. Okay, so the person what you are seeing on the slide is the person who is known by name Hans Schuster. He is the one who has got the Nobel Prize for developing a traveling the transmission electron microscope. So he is the person who is primarily responsible for the development of transmission electron microscopy, what we generally in short we call that as a TEM. Okay. So let us move on to the introduction part. Electron microscope is a scientific instrument that uses a beam of highly energetic electrons to examine the objects on a very fine scale. So we discussed two important microscopy in the last class. One is called optical microscopy, and second one is called scanning electron microscopy. To study the topology or morphology, the basic principle behind that is, in the case of an optical microscopy, it is the light rays. So whereas in the case of scanning electron microscopy, it is the electrons which are produced. So they will go into activate the electrons which are on the face, and that will be reflected back, and that will be detected by the detectors. So this is the basic principle what we discussed in the scanning electron microscopy. So here also the transmitter microscopy, but it will go one step ahead, where you are going to get it can reach up to the micros, the nano level of the atomic. Okay, so therefore, so what it says is the electron microscope is a scientific instrument that uses a beam of highly energetic electrons to examine objects on a very fine scale, very with the nano also. Okay? So that's what the electron microscopy is meant for. So now, when it comes to the transmission electron microscope. So what is the basic principle behind this transmission electron microscope? So a beam of electron is very, very thin, in the sense, in comparison with the scanning electron microscopy, so the thickness of the specimen is very, very small compared to the thickness of the specimen what we use in scanning electron microscopy. So therefore, in this case, the ultra thin specimen, we call that as an ultra thin specimen, so through which a beam of electrons is transmitted, and once the electrons passes through this thin specimen, so an image is formed from the interaction of the electrons transmitted to the specimen. In the sense, a high beam of electrons when it passes through the ultra thin specimen, that specimen will consist of an electrons, and these two electrons will going to have an interaction, and the interaction of the electrons will form an image. So the image is magnified and focused onto an imaging device such as a fluorescent screen on a layer of photographic film, or to be detected by a sensor such as a CCD camera. In the sense, so once the image is formed by the interaction of the electrons, so this image will be magnified. So imaging device might be in the form of a fluorescent screen, or it might be a layer of photographic film, or it might be a sensor, such as a CCD camera. So these are the different types of imaging screens what we are having. So any one of these can be used to magnify and focus the image which is formed due to the interaction of the electrons in the case of a transmission electron microscope. Yeah, this is just notes what we had got here. TEM is a microscopy technique in which a beam of electrons is transmitted through the alpha specimen. It is based on transmitted electrons, very high resolution. So in 1986, Ruska, a scientist, was awarded the Nobel Prize for this development of TEM. The basic principle in TEM is TEM uses a high energy electrons up to 300 kilovolts accelerating voltage, which are accelerated to nearly the speed of a light. That's what I told, a very high beam of light, a high beam of electrons. It might be going up to 300 kV, accelerating voltage. And of course, it is almost nearer to that of the speed of a light. The electron beam behaves like a wavefront with a wavelength about 1,000,000 times shorter than that of the light waves. When the electron beam passes through this thin microfilm section specimen of a material, electrons are scattered, and a sophisticated system of electromagnetic lenses focuses the scattered electrons to an image or a diffraction pattern or a nano analytical spectrum. So the same thing how we discussed for scanning electron microscope. I will going to show the sketch of a transmission electron microscope. So here also you will have the lenses, the condensing lenses. So once the electrons are produced, so these electrons are being focused onto the specimen through a set of lenses. So lenses might be in the form of a condensing lens or objective lens, okay, or projection lens, whatever it might be. So once it passes through, so the interaction of the high beam of electrons from the electron gun, and as it passes, it interacts with the electrons which are there in the specimen. So this interaction between the two attached to different electrons will result in the formation of an image. So that image will be captured on any kind of the photographic film, or what we call it as the fluorescent screen, or it might be a sensor such as a CCD camera, whatever it might be. Okay. So we have, in the case of a TEM, we have a sophisticated system of electromagnetic lenses, and these focuses the scattered electrons to an image or a diffraction pattern or a nano analytical spectrum. In this case of transmission electron microscopy, so we have a set of sophisticated electromagnetic lenses, and these electromagnetic lenses will focus the electrons which are scattered into an image, or it might be in the form of the diffraction pattern, or it might be in the form of the nano analytical spectrum. So what is this image mode? Is the one which provides a highly magnified view of a micro and nano structure. Okay, a diffraction mode displays accurate information about the local crystal structure, and nano analytical modes represents which elements are present in the tiny volume of a material. So there are three different ways, three different what we call it as the pictures you can obtain. One is called an imaging mode. Imaging mode will provide highly magnified view of a micro and nano structure. So you can see the magnified micro and nano structure. And in the case of a diffraction mode, then we're going to get the information about the local crystal structure. And in the case of a nano analytical modes, we're going to get the elements which are present in the tiny volume of the material. So this is the different, what we call it as the uses of the transmission electron microscope. So of course, I think this is de Broglie's equation you might have been studied in your physics. So where this is the equation lambda E, which is approximately equal to h divided by square root of 2 into m naught into E1 plus E by into m naught C square. So I think this you might have been used and discussed in your physics. I don't want to take much discussion over this. This is the diagram what I wanted to talk to you now. So this is a sample. Okay. So when you observe this sample through transmission electron microscope, so the electron beam, a high energetic electron beam, which passes through a sophisticated condensing lens. There are different condensing lenses. This is just a ray diagram of the transmission electron microscope. So you can have an electron gun specifically meant for producing the high energetic electrons, and we have a first condensing lens, second condenser lens, then condenser aperture, sample, objective lens, objective aperture, first intermediate lens, and then we have second intermediate lens, projector lens. So this is just a ray diagram of the transmission electron microscope. So of course we have a continued with the anode, condenser lens, sample, objective lens. So like that, so we have different sophisticated methods will be there. Diffraction lens will have projector lens and viewing screen. So like that, so you can go up to the magnification of just imagine 20 lakhs x. 20 lakhs x magnification you can get it in the case of a transmission electron. So here what's happened, just let me discuss the principle here. So we have a sample. So when high energetic beam, when it is being passed through the different condensers lens, and basically they focuses the electron beam towards the sample. So these high energetic electrons, they will interact with the electrons which are present in the sample. Basically, the samples are ultra thin films, where the thickness is very small. And once these electrons, high beam electrons, once it just engages or interact with these electrons which are present in ultra thin films, okay, so some part of the electrons will get scattered. This is called the diagram what I am showing here is a backscattered secondary electrons and elastically scattered electrons, unscattered electron beam, inelastically scattered electrons, and we have an emitted excess. And of course, we have other electrons also. So this backscattered electrons, secondary electrons, is the one which will be captured on the photographic films or the sensors. So they will going to get the images are formed, or it might be the diffraction mode or analytical modes. Okay. Yeah, this is the diagram what you can understand from how it will going to work, and I'm going to explain how this electron transmission method will work. So when you come to the working, the tungsten filament generates a beam of electrons that is then focused on the specimen by the condenser. Then we have a magnetic lens which are used to focus the beam. The column containing the lenses and specimen must under high vacuum to obtain a clear image because electrons are reflected by collisions with air molecules. Very important thing in the case of a transmission of scanning electron microscope, where we need to maintain the high vacuum atmosphere. Okay, so the purpose of maintaining the high vacuum is to obtain a clear image. The clear image, how we can get, because electrons may get reflected by the collision with the air molecules. So once the electrons are deflected, so that cannot be focused on a particular imaging screen or in a photographic screen, so that we may not get the images clearly. So therefore, so when you just maintain a vacuum, so then there will be no air molecules, and hence so there is no possibility that electrons will get reflected. Okay, so then magnetic lenses form the enlarged visible image on the specimen on a fluorescent screen. So, aside and the image captured on a photographic film as a permanent record. So high electron beam bombardment, lenses focuses onto the specimen. Electrons are used for image construction. Image is constructed by the transmitted electrons in thicker region of fluid mode. Here, one thing what you're supposed to understand, the working procedure will remain same as that of the scanning electron microscope. But what we are doing, the specimen, the thickness of the specimen is ultra thick, so that the electron beam, high energetic electron beam can reach to the depth of the atomic structure. Okay. So this is can transmit to each and every to the depth of an atomic level, and it can get the images and it can get the information which might be in the form of an image, or it might be in the form of a diffraction, or it might be in the form of a nano analytical image. Okay, so this is the working of a transmission electron. Now coming to the advantages. So this type of transmission microscopes or electron microscopes, they offer most powerful magnification, potentially over 1 million times or more. Potentially over 1 million times or more. And it will also provide the information on element and compound structure. And the images are high quality and detailed. It provides the information about the morphology, distributivity, particle size distribution, and elemental composition of the sample. This is the major advantages of the transmission electron microscopy. The most important thing is the magnification. So it is offering more powerful magnification, and it also provides the information on element and compound structure, and the images which we will going to form is of very high quality and detailed. So we're going to get more information or details of images, and also it provides the information about morphology, crystallinity, and particle size distribution and elemental composition of the samples. This is the transmission, the advantages of transmission electron microscopy. Next, coming to the disadvantages. It is very voluminous. Voluminous means it is very large, and it is very expensive. And preparation of sample is laborious, means it takes much of the work for preparation of a sample. And Operation and analysis will require special training, and samples are limited to those that are electron transparent. It requires a special housing and maintenance. Basically, it is very large and very expensive, and you need to prepare ultra thin film specimen. So, preparation of the specimen will take time and the human energy. So, laborious operation analysis requires special training, definitely, and it is limited to that are electron transparent. So, if, any specimens which are not transparent for electrons, then such kind of materials cannot be used for transmission electron microscopes. And of course, this type of electron microscopes may require a special housing and maintenance. So these are some of the disadvantages of transmission electron microscope. Coming to the applications here, of course, almost all the fields we can use the transmission electron microscopy. So wherever we require the information regarding across the atomic scale or atomic level. So whether we need the elemental structure or we need the distribution of the particles or the composition which is required. So in whatever the field, whether it is in the life science or in the medical or biological or material research, forensic analysis, in all the cases we will go for transmission requirement. And this TEM will provide topographical, morphological, compositional, and crystalline information. So topographical, of course, across the surface, composition, morphological, composition. The study of metals and to identify flaws, fractures, and damages to the micro-sized objects. So when you want to study, especially when we are doing, when we are carrying out a research on the materials, so we may need to have the information regarding the crystal structures, and we need to identify any flaws or defects are there, and what a kind of fracture it is happening and damages across the micro-sized object. And we can use samples on a molecular level, semiconductor analysis and production and manufacturing of computer silicon chips. So these are some of the advantages of applications of transmission electron. Now, the most important thing in the case of the transmission electron microscopy is the preparation of the sample. So here are some of the steps which are involved in the preparation of the sample for transmission electron microscopy. The fixation fixed with the chemical products, rinsing and staining treated with heavy metal compounds, dehydration dehydrated with organic solvents, acetone or ethane, embedding in resin, material is gradually infiltrated with the still unpolymerized resins, trimming of resin block and ultra thin sectioning, collection of sections on the film. Thin sample is less than 50 millimeter, 50 nanometer, I'm sorry, 50 nanometer. Detailed image is 1 nanometer in size. This is how we will go to prepare the sample for time. Any clarification, any doubts, anywhere if you're not able to understand, please ask me. You can stop me at any time and you can ask me. Shall we continue? Some more slides I will going to go about for TEM only. So TEM gives information about topography. surface features of the object. Morphology is the shape and size of the particles. Composition, the elements and compounds that the object is composed. And crystallographic, so information how the atoms are arranged in the object. So these are the different informations what you can get it from the TEM. And this is the main picture of the transmission electron microscope. So we have electron gun, condenser lens, we have specimen, okay, objective lens, projector lens, fluorescence. So this is just a picture of a transmission electron microscope. And here we have lenses in TEM. So we have condenser lens. There are two condenser lenses. Control how strongly beam is focused onto the specimen. At low magnification spread, beam to illuminate the large area. At high magnification, strongly condenses. So this is the condenser lens. Okay. Then next comes the objective lens. So these are the lenses which focuses and contribute most to the magnification and resolution of the image. And there are four lenses which form magnification system, determine the magnification of the microscope. Whenever the magnification is changed, the currents through these lens changes. So this is different lens systems in transmission electron microscope. Electron microscope, most important thing is the basic principle, working, advantages, disadvantages, what are the imaging modes we have, and finally the applications. So these are the important things what you're supposed to remember in the case of a transmission electron microscope. The next method of characterization technique, we call it as X-ray diffraction, or in short, we call it as XRD. X-ray diffraction, or in short, we call it as XRD. So in this case, again, we will discuss what is the basic principle, what is the working, and what is the applications, advantages, and disadvantages of this. The X-ray diffraction, or XRD, is a non-contact and a non-destructive technique used to understand the crystalline phases, different polymeric forms, and structural properties of the materials. Basically, it is a characterization technique where it is a non-contact and non-destructive technique, and it is used to understand the crystalline phases, different polymeric forms, and structural properties of the materials. So this is the basic usage of XRD. And X-ray diffraction, every crystalline substance gives a pattern. The same substance always gives the same pattern, and a mixture of substances each produces its pattern independently of the others. This is what they say. Every crystalline substances gives a pattern. The same substance always gives the same pattern. And in a mixture of substances, each produces its pattern independently of the others. Basically, when you produce or when you synthesize a composite structures, so where we have two or three different materials, one is a matrix material and another reinforcement materials. So when you have two or three different materials have been added together to form a composites. So in such cases, each material will have their own crystalline pattern. Okay, so when you just take it individually, all these different materials, so they will have their own crystalline pattern. And when they have been mixed, and each one will go to give their pattern independently of the others. They never depends on the others. What the words given by the Rontgen at the time of Nobel speech. The X-ray diffraction pattern of a pure substance is like a fingerprint of the substance. It is based on the scattering of X-rays by the crystals. So what they say, X-ray diffraction pattern, to take for a pure substance is just like fingerprints of the substance. It is based on the scattering of X-rays. So when the X-rays when passes through the crystals will scatter the X-rays. So how it has been scattered, that will be captured in the form of an image. So that is what we call it as an X-ray. I think you might have gone to the uh, diagnostic centers where you might have seen the X-rays, how they are going to take X-ray. When you come to the definition, the atomic planes of a crystal causes an incident beam of X-ray to interact with one another as they leave the crystal. The phenomenon is called the atomic planes of a crystal causes an incident beam of X-ray to interfere with each other as they leave the crystal. When a beam of X-rays incidents on a crystal, the atomic planes, okay, these X-rays they are going to interfere with one another as they leave the crystal. So that phenomenon we call it as X-ray diffraction. Now, when you look at this, what is X-ray diffraction? This is the one what you can understand here. Very simple picture here. So how X-rays are diffracted or a diffraction pattern. See, this is a specimen. Okay. So, which is been kept at an angle of 2 theta, or it is been inclined subtangent angle. Okay. So, when a X-ray incidence over this crystalline material, okay. So, this atomic level, so what we say it is the atomic planes of the crystals, they interfere with one another. Okay. So, atomic planes when the X-rays when they are just incident over a crystalline atomic planes of the crystalline structure, which causes them to interfere with each other and as they leave the crystal. So this is the diffraction pattern recorded. Okay. So all the X-rays cannot be diffracted. Some of the things will go are transmitted. So this is what we call it as transmitted beam. This is an incident beam, and this is the diffraction pattern. I think you might have studied in your physics what is diffraction. The same thing over here. Okay. So it will take at an angle of 2 theta b. I will tell you this one later. Okay. So now why XRD? The XRD basically it measures average spacing between layers or rows of the atoms. It determines the orientation of a single crystal or grain, and it finds the crystal structure of an unknown material. It measures the size, shape, and internal stress of a small crystalline features. Okay. That's why we use basically it is used for average spacings between the layers or rows of atoms. It determines the orientation of a single crystal, and most important thing, it measures or it finds the crystal structure of an unknown material, and it measures the size, shape, and internal stress of a small crystalline features. So this is the material what I have provided for you. So X-ray diffraction is a rapid analytical technique primarily used for phase identification of a crystalline material and can provide information on unit cell. Basically, it will provide the phase identification, in what phase these crystals are there. The analyzed material is finely ground, homogenized, and average bulk composition is the analyzed material is finely ground, homogenized, and average bulk composition is we can. This is the diagram what I showed in the previous same thing over here. Same thing. So once it diffracts, it gets diffracted by an angle theta. This is the diagram what they are showing here. It is a photographic, it is a crystalline solid, lead screen, spot of the incident beam, part of the diffracted X-rays, photographic plane. So this is XRD is a tool used for identifying atomic and molecular structure of a crystal, in which the crystalline atoms cause a beam of incident X-rays to diffract into many specific directions. By measuring the angles and intensities of these diffracted beams, a crystallograph can produce a three-dimensional picture of the density. This is the one what they say. And the production of these X-rays, of course, the basic principle in every atom, the electrons are at the layers or shell and the element shells. When the atoms is bombarded with an electron, I will show that later. Yeah, this is the one I wanted to talk to you. So this is how it will go. So here we have a crystal. Okay. So this is the one which will go to produce the X-ray source. Okay, so we have a diffracted beam and that will be collected over a micrographic film. This is a photographic film. So where you go to get the diffracted beams. Okay, so some more things that are given in your notes. The X-ray tubes, instrumentation, monochromator, detectors, collimator instrumentations. I think this you can study from your notes only. Bragg's law. It says Bragg's law gives an angles for coherent and incoherent. So I don't know whether you have studied this Bragg's law in your physics or chemistry. So the scattering neutron waves from the nuclei are by the coherent spin electrons and spin interaction with an unpaired electron. These are re-emitted wave fields. The Bragg's law. So if you have oh yeah, this is one picture what I want to talk. This is the Bragg's law. So how waves reveal the atomic structure of crystals. Right? This is the incident beam. This is the incident beam, and this is the scattered beam. And this is another one incident beam at an amplitude of 3 angstroms. And once it just impinges here, and this is gets scattered. This is the atomic plane. Look at this, how it is being gets into here and how it is being moved, right? So the n lambda is equal to 2d into sine theta, where d is the distance between the atomic planes, lambda is the amplitude, okay, and theta is the angle of deflection. Okay, so n is an integer. Diffraction only occurs only when the Bragg's law is satisfied. So when this equation satisfies, then only the diffraction will go to happen. So this law we call it as a Bragg's law. The condition for constructive interference, X-rays 1 and 2 from planes to space. Condition for constructive interference, how it is happening. See, in this totally it is a physics. I think these things might be you have to study in the optical physics. So the same principle here is a diffraction, the concept of diffraction what I am talking. The same thing has been used over here. This is called Bragg's law and diffraction. This is a modern automated X-ray diffractometer. Okay, so they are given the cost. It is around $560, and then we have the detectors. The modern automated X-ray diffractometer we are having. Okay. And this is the basic components and features of XRD. So production, diffraction, detection, and interpretation. So any kind of characterization techniques. So most important thing is production, the producing of an electron in the case of an electron microscopy, production of light rays in the case of an optical microscopy, and of course in the case of an XRD, the production of X-rays. So there is a one important step in any kind of characterization. Okay. And in this case, of course, in the XRDs, so we need to produce the X-rays. Okay. So then we need to have a diffraction. So as we just X-rays incident over the substrate or incident over the specimen. Okay. So once it satisfies this Black's law for getting a diffraction, so these X-rays will get diffracted. Okay. So these diffracted X-rays will be captured on a detector. The detector might be in the form of a photographic films, or it might be in the form of a sensors, whatever it might be. You can have any type. And these diffracted X-rays will going to be captured over the detectors. So these diffracted X-rays and what images will go to get it over the detectors, that is the one which will go to reveal the, what we call it as, the images. Okay, so this is the detection and interpretation. Interpretation means how it is being diffracted crystalline structures and atomic beams. So look at here: incident ray, diffracted ray, atomic blaze, diffracted crystal, diffracting crystalline. Okay, so this is the interpretation of how the X-ray XRD will go to use. And this is simple XRD pattern of sodium chloride powder. So once you just check the phases of any components here, so the pattern what you are going to get it will be in this form. So the pattern what we are showing here is it is for a sodium chloride powder. Okay, so you can see here the different peaks. Miller indices, the peak is due to the X-ray diffraction from 220 planes, sodium chloride. Look at here. So how it is being diffracted, X-ray has been diffracted, and how we are getting the peak values. Okay. The significance of peak shape in XRD, the peak position, peak width, and peak intensity. Okay. So important for particle or a grain size or residual strain. See here, you can see the peak position over here. Okay, so we can also have the Gaussian distribution over here. So when you want to ascertain, or when you want to just conclude the different phases of the compound through which you are passing an X-ray or X-ray diffraction is taking place. So the peak values, so the peak position of peaks, this is the peak position, can have a peak width, this is the width, what we call it as, and the intensity, how long it has been passed. So this is what we call it as the significance, and these peak shape are very important for us to know what is the particle, the size of the grain, as well as the residual strain. So whenever you just look at this XRD or the result of XRD or the images of XRD, so you're going to get the different peaks. So this is a graph what they have written versus intensity versus drag angle theta. So this is the one what we are going to get. So the effect of lattice strain on diffraction, peak position, and width is here. Diffraction line. So if this is the peak, it is exactly at the center, then there is no strain. And if it moves towards left, it is a uniform strain. Peak moves and no shape changes. So then it is, you need to understand that the strain is uniform. And if there is a change in the shape, a non-uniform strain, it represents a non-uniform strain if the width of the peak drops. So this is how we will go into analyze the peak shapes, peak position to obtain the different information of the Next, coming to the applications of XRD. The XRD is a non-destructive it is a electron density, and accordingly the position of the atoms in the complex structures such as penicillin may be determined from the comprehensive mathematical study of X-ray diffraction pattern. This is the one. See the structure of the penicillin. We can have a comprehensive study of the structures, the electron density, and the position of atoms in the structures using this X-ray diffraction pattern. Then elucidation of structures of penicillin by XRD paved the way for later synthesis of penicillin. The powder XRD pattern. The powder XRD pattern may be thought of a fingerprint of the single crystal structure, and it may be used for conducting qualitative and quantitative analysis, especially in the case of a forensic department. They make use of this method for just identifying the fingerprints. Okay. And XRD can also be used to determine whether the compound is solvated or not. It is one important application. And XRD is a non-destructive technique, and it identifies crystalline phases and orientations. In the sense, they are used to obtain XRD pattern, measures these spacings. This spacing is distance between the atomic planes, and it obtains integrated intensities. And most important thing, they used to compare the data with known standards in JCPDS files. And to determine the crystal's properties, lattice parameter from 10 to 4 angstroms grain size refers strain orientation, order disorder transformation, thermal expansion. So these are also some of the structural properties which you can determine by using this XRD technique. To measure thickness of the thin films and multi-layers, most important thing. And to determine the atomic arrangement, how the atoms are arranged in the structure, and it detects the limits. 3% of the phase mixture can be 0.1% with the synchrotron radiation. Will have a spatial distribution normally. So these are all some of the applications of XRD. Okay, so when you just get into the XRD results or the images, and you should be in a position to just study what these XRD results are given. So this is based upon the peak, the position of the peak, the width of the peak, and the intensity of the peak. So these are the three important parameters that needs to be considered while you are studying or while you are analyzing the XRD patterns. So this is regarding the XRD. Okay, so in today's class we discussed two important things. One is called the transmission electron microscopy, and the second one is called XRD. Okay, so if you have any clarifications, any doubts, you can talk to me. You can unmute your microphones and you can speak to me. So in the afternoon class, I will take the remaining three important three important characterization techniques. Yeah. So any doubts? Anybody want any clarification? You can unmute your microphones and you can talk to me. The students, today afternoon also we have a class. So we're going to share the link with you for joining for the class in the afternoon. So in the afternoon we're going to complete this module 4, and tomorrow I will going to start with the module 5. So module 5 is basically the concepts what you have studied in your SIM module. So majority of the parts you have already studied. So I will be moving a little bit faster so that I want to give you some more time for you to prepare for your project work also. So we hopefully will discuss much of the things in tomorrow's class regarding module 5. So any doubts, my dear students, any clarifications, you can talk to me, you can discuss with me. Okay. Okay. So if you have no doubts, or if you don't have any doubts, I will just start the class now. Okay. So we will just meet in the afternoon class at 1:45. Okay. So there I will just continue with the same thing, and I will just complete this module. Okay. Thank you.